Recording is on.
Okay, hey everyone. In this today's session, we are going to discuss a couple of problems about binary search tree and a couple of problems on balancing of the binary search tree. So basically, we going to start the complexity of BST. Last time we discussed about the finding an element in BST binary search tree and inserting a new element in BST and deleting an element in BST, and we also discussed about find in order successor to delete an element in BST. So now we are going to discuss about the complexity of these operations in BST. So let's look into that. So complexity wise, as I discussed before, so the complexity is order of h is basically height of the binary search tree. That is the best case. So um, if h is height, the complexity of BST operation is order of h. So this height depends on how you create the binary search tree. That's what I'm trying to explain. So basically, h is not a constant because as you are creating BST, as you are adding elements to the BST, the height will change. And since the property of the BST is like this, right? Any element is less than its root, and any element on the right is greater than the root element. Any element on the left side is less than, and any element on the right side is greater than or equal to the root. So as you are adding the elements, we need to decide where you need to add. So you added one here, and if you are adding two, it has to go to the right side. So if you're adding like 1 2 3 in the same order, the tree will become like this, which is not balanced here. There is no left nodes here. You are keep on adding the right nodes, and you are increasing the height of the tree. It's kind of unnecessary, but that's how we did it. So in this case, what happens, the height of the binary search tree, this is a binary search tree, and the height is equal to the number of elements. Now there is a 7 elements, and the height is also 7, right? In this situation, let's say if you want to find 7, there is no option other than searching all the elements starting from 1, because the binary search tree is formed like this. You cannot skip any of the elements. So if you're finding for 6, it could be 1, you need to compare with root, and then greater 1 is 6 is greater than 1, you need to go here 2, and 6 is greater than 2, you need to go to the right again. So you will find, if it is 7, you need to search all the elements until 7. So in that situation, so the complexity is equal to the number of elements. So it's kind of, you can think of this as the order of n. So that's why it is order of n in this. In the worst case, it's called skewed. I think skewed binary search tree. In this case, the complexity is equal to number of elements, n elements, and the worst case complexity is order of n. But if the binary search tree is balanced like this, so balanced in the sense, as I explained before, so the left elements are almost equal to the right elements. This, of course, this is complete balanced. So this balancing is really helpful to to reduce the time to find the element. So if it is completely balanced like this, let's say now you need to find 7, right? You start with 4. Okay, 7 is greater than 4. Let's go to the right. And you stay sit with 6. Okay, 7 is greater than 6. Let's go to the right. So just 3 elements. You are just comparing just 3 elements, and we will be able to we will be able to know whether 7 is there or not. Right? You no need to compare with 1 2 3 or 5. So that's why if the tree is balanced, then the height of the tree becomes log n. So this is a formula to find the height of the binary search tree, which is balanced. So the height is log n. So that's why the complexity is also log n. So that's where we discussed, and I'm just giving a very brief understanding of the complexities. So order of one, we know that order of one is very quick. So order of one means, just let me know if you want me to find an element, I can do within a fraction of seconds, not fraction of seconds, like order of one means the constant time complexity. That means, let's say if you have 100 elements, and finding an element took 5 minutes. Okay, just an example. even if it has million elements, just 5 minutes. It's order of one. I'm not changing the time to find an element or time to delete an element or any work. I want to do some work as a clerk. Let's say you're a clerk in an office, okay, and you will ask, hey, I want this file. So this clerk will go and find the file, and he took 15 minutes to find that file in the very big library of file. Okay, now I will ask, hey, how many files you have? I have 200 files. Okay, even if that library has like a, the file library of files has 1,000 elements. In that situation, if he still takes the 15 minutes to find the element, that's order of one, right? It doesn't matter how many elements you have, the complexity or the time to complete that operation is always constant. That's what order of one. So which is a very like very efficient way, but it is not possible to do in every situation, right? Only hash table is order of one. Other than that, so now the next one is order of login. So order of login is greater than order of one, but it is better. It's not order of n. Order of n means depending on the number of elements, right? So it will increase. If you have 100 elements, I will take 5 minutes to find an element. If you have, um, if you, let's say 100 elements took 1 minute. Okay, 100 elements took 1 minute, and 1,000 elements took 10 minutes, right? So it's increasing as the number of elements are increasing, as the n is increasing, right? And you are increasing the time complexity. You are increasing, you are going to, it will take longer time to find an element or delete an element. That's how it is. But log n is different. Log n is not is less than n. So that's why it is better. So that's the complexity of binary search tree. I think that's what I want to cover before going to the next question here. So is it clear to both of you guys?
Yes, Suresh.
Yeah.
Yeah, yes.
Okay. Cool. You can still see my screen, right? Great.
Yeah, yeah, yeah.
Okay. So now let's talk about this problem. Is a given binary tree is a BST? This is very popular question in the interviews as well. I will give you a tree and find out whether that is a binary search tree or not. So here we are not asking you to change anything. Don't like no need to add any elements, no need to insert any elements. I will give you a tree, and you need to say whether this is a binary search tree or not. So how are we going to do it? So here is the tree. Can you tell me whether this is binary search tree or not?
Yeah, it is.
Yeah. So because like if you, what do you do? What are we doing by looking at the tree? Basically our mind and our eyes, we started looking, we used our eyes to find that, and we used our mind to calculate. So what we did, in our mind, to find out whether this is binary search tree or not.
Whether the left descendants of the root is less than the root, and whether the right descendants of the root is greater than the root. This is the condition that the binary search tree should satisfy.
Exactly. So that is what we need to hear. So let's say, yeah, yeah, so we have this tree. Let me write down this tree here in our whiteboard for easy calculation and easy explanation. So, okay, we have the syncing alphabet here. So let's say we have this, right? So, oh, I think I lost my this thing. Just give me a minute. I will take the pen. Okay. So now, so we have this 15, right? And 3 here, and 17 here, and then 2, 14, okay, and 16 and 18. Okay, so now you are saying this is binary search tree, which is correct. So now, how about this one? Is this binary search tree?
No,
No.
it's not a binary research tree.
Why? If you look at just this one, if you look at this particular portion of it, right? It is a binary search tree because 14 is root and 19 is greater than 14, because it is a binary search tree. This is following a binary search tree pattern. But then why you said the whole tree is not binary search tree?
The super root, which is 15,
Exactly.
is smaller than 19, where the left descendants, the whole left descendants of 15 should be less than 15.
Exactly. Exactly. That's the main part here. So we need to not only just checking like a root, this is a root, and make sure this particular root is checking the, hey, left node, take the left node and compare with root, take the right node and compare with root. If this is following this pattern, and then let's go to the next one and then take the root and compare with left, take the root and then compare with right. If this is following BST, then it is a BST. It's not like that. So basically, we just, if we are comparing only the root and its left and right, and as a kind of a small independent thing, then it's not a correct algorithm. So because if you compare this 14 and 19, which is a BST, and if you compare this one, right, 2, 3, 4, which is also BST. Everything is BST. If you are comparing that small portion of it, it will be BST. But if you are taking the whole set, it's not a BST. So initially, people will think that's easy to do this. Hey, I will just compare with left and right, and then it will be easy. But it's not like that. So that's why I'm telling you how to do this algorithm. So like how to think about writing this algorithm. So now how can we do this? So how, any ideas of writing this algorithm? Because we just said this comparing left and root and comparing root and right is not a good solution, right? So I can show that solution. What I'm talking about is this is approach down. Let's do
One
this.
brute force approach is
Hmm.
we can traverse the tree, the given tree in order fashion, and store the element in an array. And if we traverse the array, if it is in increasing order, then we can say that it is a BST.
That's good, very good
But
solution. That's, I really like it.
but
Yeah.
that will, yeah,
Mm.
require additional memory.
Exactly. That is the main problem, right? So, what are we doing is we are just checking whether tree is BST or not. But in order to do that, if you are creating additional memory, this is just an nominum. Just for 7 elements is fine. But if you have million elements, you are taking another array of another million. You need to store all the elements in a array, which will take another million elements memory, right? So another problem is we are increasing complexity. Like again, not only just putting an array, you need to make sure it follows the particular order, increasing order, right? So
Yeah,
which is a
yeah.
brute force, which is a good approach, but it has its own drawbacks. So how can we do this? And you're, so putting in a separate data structure like in arrays, we are not really using the property of BST, because property of BST is clearly telling, hey, if you are on the, if you go to the left side, which is greater, which is less than, which should be less than the root, and if you are going right side, it should be greater than the root. We have that property, we know that property, but how can we utilize that property in such a way that which will be easy to find? So let me show you. I'm going to tell you how this approach one is something which we just did it. So E is BST, it says true. Okay, now I added, let's see what I'm doing here is, um, Yeah, I added 13 to the left of 16. So 16 left equal to 13. So here is what we have. So here is the, okay, let's do control Z. Do we have control Z? No. So what I'm doing here is, so in the, okay, let me remove this. Let me remove this, and this. Okay, so we have this tree. So this is binary search tree. Now if I add 13 here, that's what it did, right? Yeah. If I add 13 here, right? So if you look at this particular part, it's still BST. If you look at only this part, right, this is BST. But if you look at the whole part, because 13 should not be on the right side of 15, correct?
Yes.
So that's where it failed, right? So it should not be part of this. It should not be on the right side of 15. So now, but if you go with the approach one, look at the answer here. So initially this is binary search tree is true, but after adding, so here is the thing. I added element, and again I used approach one. It says it is still BST because this is wrong. So let's see what is inside that approach. Is BST approach one? This is this is very common. Everybody try to write the code. If you are an entry, you will write the code in a similar way. So basically, what we do is tree BST approach. This is the Boolean, and then is left tree BST, is right tree is BST. We are putting two Boolean variables equal to true and true. Initially, we are thinking true. Now, what we are doing here is, hey, is the root, is this particular element has some left element? Yes. If you have left element, let's compare the value of the root with left element. So root dot value greater than root dot left dot value, then is left subtree, is left subtree BST equal to is tree BST root dot left. So basically what are we doing here is, it is really important to understand, even though this algorithm is wrong, we need to understand what are we doing here. It will help us to understand the other algorithm, which is good, which is working fine. So here what are we doing here is, we are checking, is this particular element has left node. If we have left node, is the value of the left node is less than, or maybe you can think of this way, is the root is greater than left or not, right? So which is like, this is the main condition of BST. Root needs to be greater than left node, correct? If that is not the case, we are simply setting Boolean to false. We know that. Let's say this one has 33. It's not 3, which is 33 here. So left node is greater than, like root node 15. Like we are checking like this. Is 15 less than 33? Right? That is the condition here, right? Root dot value is greater than, sorry, we are checking like this, greater than. So is root greater than left value or not? Which is not, right? Because we have 33 here and we have 15 there. We are simply saying left subtree is BST equal to false. We are saying, okay, if you consider left side, it's not BST because we have 33 on the left side and you have 15 on the root, which is violating the rule of BST, right? We are setting as equal to false. Similarly, we are comparing the right side. If the root, we have right side, is that particular element has right element? Yes, there is a right element. And now we are checking, is the root less than or equal to root dot right dot value, less than or equal? So that means, let's say you have 17 here, right? So 15 is less than or equal to 17. Is it right? Yeah, which is right, right? Let's say you have it's not 17. Let's say you have 7 here. Just assume that 7 here. So what happens? 15 less than or equal to 7? No, right? So in that situation, it is not binary search tree. Either if this condition failed, we are checking whether these two are properly, set agreeing with the BST rule, or is these two are properly aligned with the BST rule? If any of these fails, right? If any of these fails, what happens here is we are putting under condition here. Is left sub tree and is right sub tree is BST. So basically we are checking whether both are. If any of this becomes false, what happens? The under condition, the whole under condition becomes false, right? So let's say you have 17 here. Let me remove this. We still have 17. So if you go with the right side, it is following the BST, which is good. But we have 33 on the left side, so which is not following BST. Correct? So this is the under condition of these two. One is false and another one is true. What happens? The final condition, true or false? If one is false and the other one is true, if you are putting
False.
condition is false. So that's what we want, right? So this is, at least this is failing the, this is 33, which is failing the BST rule. So we will say simply this is not a binary search tree. We no need to check any other nodes. But in this situation, let's assume that it is not 33. That's what it here. Let's go back to our initial problem, which is not 33 here. We still have 3 here and 17 here. That means this is 3 here, and what happens here is both are true. Okay, this is following BST rule and this is also following BST rule. So both are true. So 15 is greater than 3 and 15 is less than or equal to 17. Both are true. Then we can simply return true. But no, is that right? We should not return. We need to check the remaining nodes of the tree, right? We just started with root. We need to check 2, 4, 2 and 14. We need to check 16 and 18. That's why what are we doing here is, if this condition satisfies, we are calling the same method recursively. Basically, we are making, now this is a root. Let's assume this is a root and then compare the remaining nodes of the left. That is what this line number 103. So if this is satisfying, if the root is greater than left value, that means it is completely satisfied the rule of the BST. Let's check the left. Basically, we are calling the same method is tree BST. I should call this one actually. It doesn't matter, I guess. So I should call this. Oh wait, is tree BST. No, yeah, I think. Okay, I think I did a mistake here. So I think we need to call the same approach one, right? We need to call the same method, same recursive function by changing the root node. Since we already checked 13 and 3, 15 and 3, let's check 3 and 2 and 3 and 14, correct? We are calling the same method. It's kind of sub problem. It's a, now you are considering 3 as root and calculate the rest of the tree under the 3. So that's what we are doing. So now, and then finally we are assigning the value to this boolean variable. So we don't know whether any of these following or not. So we need to see, even though 13, even though 15 and 3 follows the BST rule, this could be, let's say if this is 12, this is failing, right? So that's why we cannot simply say this is true. So that's why we are saying is left subtree is BST. So it will go to the recursive method and verify this 3 and 2 and 3 and 14 and everything. And finally, it will give you whether true or false. It's a recursive function. It's very difficult to understand. I'm trying my best to give what is happening here. So let me know if any questions. So basically, once this rule is satisfied with one element, we are checking the left. We are checking the next, branch of the tree. Basically, we are going left again and verifying whether the whole left branch or left subtree is a BST. Okay. Similarly here, if the right element is satisfied the BST rule, we cannot simply assign true. Even though these two are satisfied, any of these elements may go wrong, right? That's why we are not setting true immediately. We are calling this function and asking, hey, check whether the remaining elements in the right side. Finally we will get the true and false, and then we are saying okay, everything on the left is true and everything on the right side is true. Then it is finally returns whether true or false. It looks almost like a correct algorithm, but there is an issue here. So is this algorithm is it clear, or any questions so far? I know it is complex.
It is clear to
No,
me.
it's good.
So basically what are we doing, just trying to understand like what is the existing algorithm is doing. Okay, it's building. So let's see if I get the same answer. So yeah, see this. So this is approach 1. The initial tree is fine, and after adding 13, so what I'm doing here is I added 13 to the left of the 16. So that means, so even after adding 13, right, it is returning true, which is wrong, right? Look at the answer here. After adding 13, right, result 2, approach 1, and result 2 is still is saying, oh no, this is one approach, yeah, approach 1. So it is saying like, so result yeah, wait, okay, this is 15. So approach 1 is tree BST, is tree BST. Yeah, this is what I'm talking about. So if you call approach 1, both will return true. Okay, which is good. So if you call approach 1 in the approach 1, which is good. So but now I added 13 here. See, after 14, 15, that this is in order, right? As Arvind mentioned, we put everything in order. I'm just printing in order way. So we got 2, 3, 14, 15, and then 13, because that's what the in order, right? In order of this one is like this. We need to start with 2, 3, 14, 15, and then 13, 16, 17, 18, because that is the in order. So that's how it is. So look at the in order: 2, 3, 14, 15, and then 13. Now if you call the approach 1, it is still saying it is BST. But if this is the right algorithm, is BST, is tree BST is the right algorithm, I'm going to explain pretty in a minute. But the approach 1 is false, right? Because it's saying like, hey, even after adding 13, it is written as true. Why? Because we are only checking. So we checked it 15 and 17. Okay, we are thinking it is true. Now we are asking to check 17 and 16 where it is true. Now we are checking 17 and 18, which is true. After that, 16 and 13, which is also true, right? We got true, 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 everything true. Anyway, left side is already true. Left side there is no problem. Two, it's the elements already in a proper way. So now we got the final true, right? So all the elements here is also true, and all the elements we giving true, and finally we are assuming that the whole algorithm is a BST. Since we are only checking, we are not checking 15 and 13, right? We are not even checking 17 and 13. We are only checking 13 and 16, which is following BST rule. That is the problem. Okay, are you guys understand? I want to make sure you guys understood the problem of the existing algorithm what we have. Karini, I think you just joined. Will you
Yeah.
be able to see the screen?
Yeah, yeah, yeah.
Okay. Yeah, go ahead, Arvind.
Yeah, so basically we are just checking the root and its left and right child, not
Child.
I mean all the
Ex-
ancestor of all the
Ancestors.
children, like children of children, like that
Exactly.
order we are not checking.
Exactly. That is the main problem with this algorithm. When I like 3 years ago when I started writing with I did not look any websites. I just started writing like this and I said, okay, it's done. But it's not, because this is the problem here. So we are not checking 15 and 13. We are not checking 17 and 13. Like we need to check all those. So now I understood the problem. So now how can we solve this? So we can do one way. In a brute force way, let's check 3 and 15, let's check 2 and 15, let's check 14 and 15, and again Then if you're on the right side, let's check 15 and 17, let's check 15 and 16, let's check 15 and 18, and 15 and 3. Okay, now we are done with 15. Now if you come to 17, again 17 16, 17 18, 17 13, it's like, see, there is a repetition happening there, right? So how can we, is there any way to do this in a better way, right? So
Yeah.
so we need to find a better way to check the check this algorithm whether this particular is a BST or not. Karan, are you following so far? Did you understand like the
Yes, yes, yes. I'm following.
yeah? So we can do this way. So I'm revealing the code, I want to see how can we what is the way to explain. So um, yeah, yeah, I think I got the idea here. Yes, we should have something like this: lower bound and upper bound concept. So what is meant by that is, let me remove all these things here. Maybe I can draw again. So what is the best way to do this is, basically we need to, we will still go with the iterative, like not iterative, recursive way, but we need to find a better way of doing it, right? So we have tree like this. This is 16 and 18, right? And we have 13 here. So 13 will be added after. So now what we need to do is, okay, yeah, let me explain, starting with let's see, yeah, 13. Let's start with 13. So 13, we have 13 here, right? So there is a condition here. So what is the condition here is, let's look at the, right subtree. This is a right subtree, right? In this, if you look at observe carefully, there is a property, there is a inherent behind inherent logic here. All the elements greater than 15. What is meant by that? That is the main, this problem here is 13 is not greater than 15. That's why it is not BST, right? So all these elements under, like, whichever the elements I circled right now should be greater than 15. That means you can think of as a 15 as a lower bound. Lower bound means it kind of, it's kind of checking condition. Everything on this is greater than this one, greater than this particular 15, right? And what is the upper bound? Upper bound, there is no limit. You can have 1,000, there is no limit, right? Because you can have 1,000 here, you can have 999, there is nothing like that if you compare with 15, right? Because anything greater than 15 is fine, you can put on the right side. Now if this condition failed for 13, correct? Now come back to the left side. If you come to the left side, let me put another color on the left side, which is these trees algorithms are really tough to understand. Bear with me. So now look at the left side. What is the condition here? Left side, what are we saying is all the elements should be less than 15. So here is the lower bound LB, and there is no upper bound. There is no upper bound, right? For the right side, there is no upper bound. You can put any element. Only condition here is that element should be greater than this 15. So 15 is kind of lower bound, and upper bound is anything. Now come back to the left side. Here is the thing. All the elements should be less than 15. That means here is upper bound. There is upper bound 15. You cannot have any element greater than 15. Okay. But there is no lower bound. You can have anything. You can also have -0 and -5, -10. You can have -1,000, right? There is no problem. You just imagine that these are all integers. Okay. Just integers. And now you can have any element which is less than 15. That means there is no lower bound. Only condition here is upper bound. This particular property is very important. So because that's what we need to tackle here, right? You don't compare just with root. Comparing with just root is useless, right? So you now if you compare this upper bound lower bound concept, then you will see, right? So now 13 is failed, right? 13 is here. 13 is which is less than 15, but which is not following this upper bound rule here. So that's why we can simply say it is not a BST. So how can we do this? How can we do this is basically,
Suresh, I have a question here.
yeah, go ahead.
Yeah, so that lower bound and upper bound,
Yeah,
will that change for every level, or should that be constant like?
exactly. It will change for every level. That's good question. So now, sorry, complete your question. I don't want to distract actually. So is that the question?
Yeah, that was the
Yeah,
question.
yeah. This lower bound, upper bound will change for every recursive algorithm. The recursive checking. That means, let's say we don't have this left side. We have only like this 17, 16, and 18. When you are recursively doing only 13, okay, this is the only thing we have. Okay, this is the tree. You compare with 15. Now what happened here? Now again, this particular 18 has its own lower bound. 18 and also all the children of 18. What is the upper bound here? 17. Because you started, this is the rule. This is the whole tree you are checking, right? Now the the lower bound becomes 17, not 15. Okay.
Yeah,
So similarly, that upper bound, there is no limit. That is very important here. So now if you are checking for 16 and 13, 16 and 13, what is the upper bound? Not 15, 17 here. Because for every time when you are doing, that is very important. Because when you are calculating up in this time, if you are going right side, there is no upper bound. Right side, there is no upper bound. Similarly, if you go left side, there is no lower bound. Okay, only lower bound is for right side and upper bound is for the left side. So it will keep change. Okay, so now how can we do this? That means every time, so basically, of course we don't need lower bound here, but we need to have that condition. We need to check with this, right? Even 2 is like, let's say 2 3 is here. What are we checking? Whether 3, initially we checked with the left side and we checked with the right side. But now we
So,
need to check with lower bound and upper bound, right? Go ahead. Go ahead,
yeah,
Karna.
finding for the right side,
Hmm.
finding the least uh, element, finding the least element and compare it with the upper one. Will it work?
We can do that, but finding the least element itself is a lot of processing you are doing,
Okay.
right? So
Yeah.
let me explain this way. So now just yeah, we are very close to the final algorithm. So let's explain this way. So we need to compare with lower bound and upper bound every time. That is for sure. We need to compare with lower bound and upper bound, not with left node, right node, or anything. Of course, we will go with the tree in left node, right node pattern, but comparison needs to happen with upper bound and lower bound. So this is how it happens. Okay. Now take 15 and 17. Okay. So 17, since you are going right side, we know that lower bound is there. Okay. Lower bound is 15 and upper bound is equal to anything, infinity. Because because as long as this particular element you are checking is less than this element, we are good. This is lower bound, right? Now for 18, if you are checking 18, 18 needs to lower. What is the lower bound for 18? 17. And upper bound is infinity. Max number of, like whatever the max of integer, like let's say this is integer kind of thing. I think 32,000 or something, right? If you look at the memory wise, you can store certain number, which is the max number of integer in the data types, right? So that's the max you can store. right? So lower bound is for 18, lower bound for this node is only 17. So at any point of time, we will compare with lower bound and upper bound. So if you go with the right side, lower bound is the root node, lower bound is the root value, but the upper bound is unlimited or the integer dot max. Let's say integer dot max here. You can have max number here. That is upper bound. So any element, if the element is less than, if the element is greater than the root and less than or equal to this integer dot max, this element is in a right position, in a right way. Correct? Now what happens? We checked 17 and 18, which is also good. Now compare 16. For 16, what is the lower bound? Again 17. No. Wait. 16. No, 16 we have upper bound. Sorry, this is the problem. You went left side, right? If you went to the left side, we know that 16, whatever the value here, see, whatever the value here must be less than 17. We know that. We have upper bound. Correct? We always have upper bound. If you are going left side, we have upper bound here. But value can be anything. It can be like it can be anything integer dot. No, wait. I am wrong here. So this is the condition. For 16, it will have both upper bound and lower bound too. It will be 15. So basically this lower bound, whatever the lower bound here will come here, and the upper bound will come here. The root becomes the upper bound. So whatever, if you are comparing 16, it needs to greater than this number and less than this root. That's what we are doing, right? If you are looking at 13, 13 should be greater than the upper bound. Lower bound. Lower bound is 15, but greater than the lower bound 15 and less than the root value. That is where it is failing, right? What is the lower bound for this whole right side? 15. Less than some value here. It should be again. So it's not less than. Sorry, this is a lower bound, right? Yeah, that's right. It should be less than, and then it should be again less than or equal to the root value. Root value is 16. So whatever you are putting here, which is now we have 13, is it following our rule?
No.
Because lower bound is 15, upper bound is 16, which this is following. 13 is less than or equal to 16, which is good, which is true. But this is false, right? That
Yeah.
is where we fail. So for every element, when you are checking with every element, we not only just check with the root value. We also check with the lower bound. Okay. Yeah, that is the complexity of this algorithm. Let me show you the algorithm. Maybe if I show the algorithm, that might be easy to understand. So what the thing here is, as Arvind asked, like we need to keep change the lower bound and upper bound properly. That is also very important. Okay, I'm trying to find an example of that. Yeah, let's look at the algorithm, then we can easily understand. So this is what we did: is tree BST. Okay, this is the runner of the algorithm. What are we doing here is, so we need to put integer dot min value and integer dot max value. We are creating another method, is tree BST. Let's close this wrong approach. This is wrong method, and here is the right method. This right method has three parameters. One is the value, the root, and min and max. This is the lower bound, this is the upper bound. Okay, so when you're starting with root, okay, what is the lower bound for root and upper bound for root? There is nothing, right? So the only thing is, of course, there is a one thing, like the value here is like less than integer dot min value, min value. This the min value is less than or equal to value, and this value is less than or equal to max value. That is the only condition, right? So anything is possible. You can put any number as root. There is no restrictions as long as the number is between the integer dot min and integer dot max. This particular root is BST. Let's say this is this BST 50. A tree with just one node 50. Is this BST? Yes.
Yes.
Right? Because it is just, is it between integer dot min and integer dot max? That is the only condition. Of course, there is no left node, there is no right node. So, but the condition here, it needs to be between those two bounds. You cannot add any characters there. This is integer data type. That's what we are doing here. So, we are putting lower bound and upper bound, and we are checking here. Let's look at the algorithm now. Simply, if the root value is null, return true. If the root value is null, means like you reach, either there are two conditions, either there is nothing, no elements in the tree, or you reach the end of the leaf node. If the if you reach the leaf node which does not have any left or right, you simply return true. Otherwise, we are checking with this condition. This is the another condition. As I said, is root value is less than min. If root value is less than or equal to minimum value, or root value is greater than maximum value. This is the lower bound and this is the upper bound. So return false, because the value must be between these two, right? As I just said, the value of the root must be between this min and max. Okay, if any of these condition fails, if the root value is less than or equal to min, root value must be greater than min. If it is less than min, false. Or if the root value is greater than max, that is false. So this condition will be verified probably for 13. When we are checking for 13, what happens here is, when we are checking for 13 as the root, and the min value should be like this, I guess. Yeah, max value is infinity and min value should be 16. No, yep, min value should be 15. We will get 15 here. So 15 is less than or equal to 13. So here root value is less than min. Oh, sorry, I think I was wrong. No. Here the max value is 15, I think. So we'll see. Anyway, when we run the problem, we will see. Yeah. So root dot value, if you are looking at the root dot value is 13, 13 should be greater than max. Yep. I think the max will become 15, something like this. So yeah, we'll come to this here. So if any of these fails, return false. Otherwise, check the subtree recursively, and tightening the min and max constraints allows only distinct values. So this is only distinct values. Basically, if the values are same, this algorithm may not work. So whatever we're doing here is, so here is the left side. We are checking with the left. So we compared root. Root is following the conditions. Now we are going to the left node here, root dot left, and minimum is always minimum, but root value -1. This is the way we are changing the upper bound. So what are we doing here is, you compared with this. Okay, let me clear again. So you compared 15. Now you are done with 15. Now you want to go to 3 left side. If you want to go with 3, what are the conditions? What is the min and max? For 15, min is integer dot min, and for max is integer dot max. Right? What is the condition for 3? For 3 is, look at the 3. 3 is minimum, anything. So min again for 3. Oh, 3 is here. For 3, minimum, this part, the value of this node can be anything between these two. Between these two means integer dot min and max bound is 15 minus 1. That means 14. which is 14. So this value can be anything between these two, right? Between the integer dot min and 14, correct? You can put 14 here, not a problem, right?
Yes.
Is it right? Yeah, that's what we are doing here. So that's what we are checking. So we are just checking like -1. We are decreasing the value of the root, because anything left side of the root is any value less than the root value, right? That's why we are checking 15 minus 1, and anything, this value can be between these two. It could be minimum value is again a min, and the max value here. So, and right side, if you go with the right side, we will increment the root value. Root value plus 1 and max. Max will stay there. So the max value here is integer dot max here. So anything here, anything on this one is, it could be between 16 and max, which is good. 17 is between these two, right? 17 is here after 16, and then we will come to the next one. Okay, so now if you observe carefully how this algorithm works for 17, we just checked for 17, right? Let's check for 16. So when you are checking for 17, what happens here is you call like this. I think it is better to write the signature of the method, then it will understand. So we are checking 17 with two values. So let's start with 15. So if we start with 15, it will be very easy to understand. So we are checking with, oh my god, it's tough to clear. Okay, so now what are we going to do here is 15. Let's start with 15. When you are checking with 15, this is integer dot min. It needs to between integer dot max. This is the min and max. Now when we are checking for 17, right? What is the minimum value? 15 plus 1. 16 is the minimum value, but max value is anything, correct? When you are checking the value here, it needs to start with 16, because 15 is the root. It can be 16 here. It can be any value between 16 and integer dot max, correct?
Yes.
Are you guys following? Now when you are checking for 16, this is followed. This is true. This is true. Now when you are checking for the node here, it needs to be, so when you are checking for 16, node 16, it needs to be, what is the minimum value? Minimum value here is same minimum is minimum, because we are not changing, right? If you are going left side, if look at this, we are not changing minimum, only we are decreasing the root value. That means root value, what is the root value here? 17, right? 16 and 16. So when you are checking the value here, it must be between these two. There is no other value between, right? 15 is here, 17 is here. That's the thing. You cannot put any value other than 16 here. If the tree allows only integers, right? You cannot put anything in the left side of 16, because if you go to the left side of 16, what happens here is like this. 16, the minimum is, okay, here what happens if you are going left side of 16, and then what happens? Minimum is minimum, which is 16, and root value, if you are decreasing to 15, okay, now it will fail the condition. So if you are checking for 13, sorry, I think if you are checking for 13, this is the condition. So what happens here is, you are checking for 13. 13 needs to be between 16 and 15. Is it possible? So 16 is
No.
between 16 and 16, which is possible. 17 is between 16 and max, which is possible. 15 is between min and max of integer, which is possible. But 13, if you want to put 13 here, it needs to be between these two integers, which is impossible. This is a minimum. We are saying 16 is minimum. This is minimum, and maximum is 15, which is not even correct actually. Like, how can we make 16 is minimum and maximum is 15, and how can we find an integer which is satisfying this condition? So that's where it fails, right? If you calculate 13 becomes, right, if you are calculating 13, what happens here is root value is 13 and minimum is 16, maximum is 15, and here root value is 13 less than minimum, root value is 13 less than 16, or root value is greater than maximum, root value is 13 which is greater than 15, so return false. So 13 less than 16, right? 13 less than 16, yes, this is true, and this is false. If 13 is not greater than 15, but once this is true, then we are returning false. So finally we'll get the answer as false. Okay, so you are checking something, you are checking, you have a root value 13 which is less than the minimum. What is the minimum here? 16, right? So you just simply here, you can put anything, you can put anything here which is less than 16. So minimum is 16, but max value, okay, I think this is still true, this is true, or root value, okay, root value 13, this is false here. So finally it becomes false. Okay, so you guys following, right? Basically we are checking with lower bound and upper bound. Yeah,
Yeah, this is a very good approach.
yeah. So basically when we are going with each and every element, we need to set the minimum value and maximum value. This way we can easily find whether we are in a correct way or not. So we can do one thing. So you can put a breakpoint here and see, start with debugging. So because if the root value is 13, then we will see the min and max. Okay, now let's continue here. Okay, look at the false here. Why it is false here is root value is 13. I told you, right? Root value is 13 and minimum is 16, maximum is 15. So how can we do that? We cannot put in any value like that. So minimum, it needs to be like this. It should be 15 is minimum and 16 is maximum. You can put something like 15.5. That is possible. If this allows decimal values, you can put 15.5, because 15.5 is greater than this one, right? That's a and less than 16, right? So then if the root value, let's say if the root value is 13 here, 13 is less than 16, yes, that means this condition is following. If you compare these two, if you compare just these two, 13 and 16, it is following the BST rule. But is it following the other one? 13 is greater than 15? No, right? That is 13, you are putting a 13 on the right side. Is this 13 greater than 15? Which is failing, right? Now if you have 15.5, 15.5 will, okay, 15.5 is less than 16, which is okay, because you are putting on the left side, which is less than 16, which is good. And is 15.5 is greater than 15? Yes, because it will satisfy both the conditions. If instead of 13, if you have 15.5, it will success, it is a BST. Correct? Are you guys following so far?
Yes.
Yeah,
Yes, Suresh.
yeah, that's how it is. So basically that it's a complex part, but the only thing is just few lines of code, just to understand how simple writing of the algorithm is easy. You can by heart this, even if you're going for an interview, you can by heart. But the only problem here is how it works is important. If the people ask, hey, what is, you are just, it looks like you are just by heart and wrote the algorithm, but how it works, that is really important here. So you should be able to explain that situation, how it is happening, and if you say that if it is 15.5, then it is, it is BS, then he can definitely understand. Okay, he know the algorithm. He's clearly understood what this is doing. Basically, whenever you are checking anything, we always need to remember the root value. We always need to make sure this is between those two bounds. As I said in the beginning, all the elements here, the the left bound is 15. That means that all the elements should be greater than 15, but the element should be less than whatever the element you are checking on the root. That is the only condition. If you're checking for 13, 13 should be the value here greater than the 15, but it needs to be less than 16. You are just checking with the root, and also you are checking with that condition, the max and minimum conditions, the bounds, actually left bounds and lower bounds and upper bounds. Of course, that's called min and max basically here. So now if you look at the algorithm, it clearly says, right? So the second algorithm, like if after you adding 13, it says result to false. Is the tree BST? No, because you added 13. Okay, is it clear? I know it is
Yes.
complex. I know it is complex, but it is, yeah. So it's
Yes.
almost like 9 o'clock. Shall we wrap up or shall we continue other one? Maybe it might be 10:30 for you guys, right?
Yeah, it's 10:30, Suresh.
So shall we continue the next week about the other algorithm, the tree
Yeah,
balanced? Yeah.
yeah, sure,
So
sure.
Yeah.
cool. Yeah, I will share the code link of this code, and you guys can look into this. Okay. So
Suresh, where is this taken from? Like page number 110.
oh yeah, this is basically the CIC, this one, the cracking the coding interview.
Okay, okay, okay.
I don't know whether you have that book. So this is the book, actually, the cracking the coding interview book. It's better to, better to have. It's a really good book, actually. Yeah,
Okay, okay.
yeah. Okay, I will send the link of the book as well if you guys want to buy it. Yeah. Okay, cool guys. I think this is a really good session. I hope. Um,
Yes, Suresh, thank you so much.
Yeah,
It's
yes,
really
Suresh.
complex,
yeah,
but
really
good.
complex to understand, but if we can focus clearly what is happening, its best way is we use use any of the the algorithms, the IDEs, and put the breakpoints to understand, and pen and paper, very important to run with pen and paper. So when you are working in these algorithms. Okay,
Okay.
cool. Okay, talk to you next week.
Thank you so much.
Have a nice day. Have a nice week.
Thank you,
Yeah,
Suresh. Thank you.
thank you. Bye.